Alright, this is The Incredibles book, page 199. This is like my fourth attempt of writing this, so sorry I started already. Alright, but it's pretty easy. Alright, so we start with the domain. It's easier to say what is not in the domain. You have a fraction, you just only want the denominator equal 0. And here, x equals 3 will make the denominator equal 0, so we don't want it in the domain. So it's everything except 3. Alright, range, we're going to do last, so don't worry about that. X-intercepts, we just want to set this equal to 0, right? So we're solving the equation x squared minus 3x plus 9 over x minus 3 equals 0. If you have a fraction equal to 0, the only thing that needs to equal 0 is the numerator. X squared minus 3x plus 9 equals 0. We don't need a denominator equal to 0. And we've already dealt with that when we talked about the domain. But anyways, all right. Try to factor this, and I can't. So let's look at the discriminant. If you remember, the discriminant is b squared minus 4ac. So b is 3. So it's negative 3 squared minus 4 times 1 times 9. And that gives me 9 minus 36, which is negative 27. If the discriminant is negative, there is no real solution, so this has no solution. So there are no x-intercepts. None. Not applicable. All right, y-intercept. For y-intercept, all you're going to do is plug 0 in for x, and you get 9 over negative 3, so you get 0, negative 3 is your y-intercept. Symmetry, I'm not going to worry about. Horizontal asymptote. The degree of the numerator is higher than the degree of the denominator, so there are no horizontal asymptotes. Vertical asymptote, you want to set the denominator equal to 0, and that it does not cancel with the numerator. It doesn't cancel, so we have an x equals 3 is the vertical asymptote. Now we take the derivative, so I'm going to do the derivative on scratch paper. I'll do that in a second. You have to use a quotient rule for this one. So let's do that over here. Copying the problem first. F of x equals x squared minus 3x plus 9 over x minus 3. Alright, so we're going to apply the quotient rule here. Let's see if I can make this fit. Alright, so f prime of x equals, bring up the denominator, times the derivative of the numerator, minus derivative of the denominator, times the numerator. All over denominator squared. Okay. So this is the x minus 3. I brought it up. 2x minus 3 is the derivative of the numerator. Derivative of the denominator is 1, right? It's always a minus here for quotient rule. And then times the numerator. X squared minus 3x plus 9. All right. Now I'm going to clean that up some. Clean that up. I'm going to multiply out the first two terms, or at least this part. So that's going to be 2x squared minus 3x minus 6x minus 9x plus 9. Distribute that minus, so it's minus x squared plus 3x minus 9 over x minus 3 squared. Continue with that. The 9's cancel. Negative 9x and positive 3x gives me negative 6x, 2x squared minus x squared. So it's x squared minus 6x over x minus 3 squared. So that is the derivative. So we put that here. So the first derivative is x squared minus 6x over x minus 3 squared. Excuse me. All right, critical numbers are x equals 0 and 6. How do I get the critical numbers? You set the derivative equal to 0. So we could just say, when is this equal to 0? Remember, if it's a fraction, you don't need the denominator. So just x squared minus 6x equals 0. You could factor that. That's x times x minus 6. So x equals 0 and x equals 6. And that's how I got those values. X equals 0, x equals 6. Let's. You might be wondering, why do I have a 3? So remember, whenever there's a break in the domain, you want to put that on your sign chart because that will affect that may have a sign change in the derivative. All right, so plug in numbers left of 0 into this expression because we're checking the first derivative. This is the sign chart for the first derivative. So say -1. So that'll be 1 plus 6, so it's positive. Plug in a positive 1. 1 minus 6 is negative. You notice I haven't been putting it in the denominator, but if I put it in the denominator, there's a square on it, so no matter what happens, it turns positive. So only the numerator is going to give us a sign. Plug in the 4. 4 squared is 16 minus 24 is negative. Plug in 7. 7 squared is 49 minus 42 is positive. So that's the sign chart. So it's increasing from negative infinity to 0 and 6 to infinity, right? This is where the derivative is positive, so it's increasing there. It's decreasing between 0 and 3 and 3 to 6. And we definitely don't put 0 to 6 because at x equals 3, it's actual break. There is a break in the function itself, so we can't include 3. So there is a minima at x equals 6, and there's a maxima at x equals 0, right? There's a minimum at x equals 6 because the derivative changed from negative to positive. At x equals 0, there's a maxima because it switches from positive to negative. In other words, it's going up and then going down, right? If you want the y values, all you're going to do is put it back into the original function. And we should probably do that. So if we put in the original function, that'll be 6 squared minus 3 times 6 plus 9 over 6 minus 3 is 3. Excuse me. 36, 18, 27. Divided by 3 is 9. So it's at 6, 9. And plug in 0 and I get -3. We did that earlier when we did the y-intercept. All right, I'm copying the first derivative. Oh, sorry, there it is. Oh, I hope you guys saw that. Just plug it in. Sorry, first derivative. I'm just copying it. This is for convenience. Like if you were doing the work, you don't have to write it again. All right, now let's take the second derivative. That requires quotient rule. So I'm going to do that over here on scratch paper. Hopefully I'll do it so you can see it this time. So here's the first derivative. All right, that's the first derivative. Let's take the second derivative. So bring up the denominator. So it's x minus 3 squared times the derivative numerator. So it's 2x minus 6 minus derivative of the denominator, which would be 2 times x minus 3 to the first times the derivative of x minus 3, which is 1, times the numerator, which is x squared minus 6x, over the denominator square, so it's x minus 3 to the fourth. All right, now let's clean this up. I'm going to factor out an x minus 3. Okay, factor out an x minus 3. Anything else come out? I don't know. All right. I don't see. All right, so when I take an x minus 3 out, it's going to leave me x minus 3 and 2x minus 6. And that's going to leave me minus 2 times x squared minus 6x. Okay. So I took x minus 3 out of both of these parts, right? When I say both of these parts, I mean this part and this part. I took out an x minus 3. When I take an x minus 3 out here, it leaves me an x minus 3 and a 2x minus 6. Here, it leaves me 2 and x squared minus 6x. All right, now I'm going to clean that up. So that's going to be... So here, I'm going to cancel the x minus 3 and x minus 3 to the fourth, so leaving me x minus 3 cubed in the denominator. So I got to multiply x minus 3 times 2x minus 6. That's going to be 2x squared minus 6x minus 6x, making it minus 12x. And then negative 3 times negative 6 is plus 18. And I'm going to distribute this minus 2, so it'll be minus 2x squared plus 12x. All right, so 2x squared minus 2x squared cancels. Negative 12x and positive 12x cancels, leaving me 18 over x minus 3 squared. That's the second derivative. Excuse me. There is that. All right, so critical numbers for the second derivative, none. But we're still going to put the 3 in the sign chart. And it's positive on both sides. So it's always concave up. So we say negative infinity to 3 and 3 to infinity. It is concave up. Whoa. Whoa, 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 whoa. Something is wrong, isn't it? Come on. I wrote 2 here, but it's a 3. It's cubic. Okay, so I made a mistake. Sorry. So that's third power. And in fact, it's the opposite. It's going to be negative and positive. Right? To the left of 3 would be negative. To the right of 3 is positive. So it's in fact only concave up from 3 to infinity and concave down from negative infinity to 3. There are no points of inflection because where it does change concavity, 3 is not in the domain. So there are no points of inflection. All right, now let's graph this. So we have a vertical asymptote at x equals 3. Is this too small? All right. X equals 3, there's a vertical asymptote. There's no horizontal asymptote, there's no x-intercept, there's a y-intercept of 0, negative 3. 1, 2, 3. And in fact, that was a max. All right. And then there's a min at, what was it, 6, 9? 5, 6, up to 9. Okay. So the graph over here, up here, looks like this. And it was concave up, that's a min. And then over here, it's concave down, and that's a max. And so that's what the graph looks like. Okay, that's it. I'm going to do the other one, the next problem on another video.